Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be talking about multisets, which is a mathematical construction used to denote a set with repeated elements allowed. So let's go back to the making choices question from the last video. The central question we were working on is how many ways are there to select k things out of n possible things? And to clarify this question, we need to know whether our things are unordered or ordered, and whether no repeats are allowed or repeats are allowed. We had ways of figuring out the formula for these three entries of the table, but the fourth is a little more complicated. So an unordered choice with repeats allowed is called a multiset. We're going to denote this choice with the symbol double choose here, or multi-choose, where you put two parentheses instead of one parentheses, and it's just the symbol we're going to use, and we're going to find a formula for this in terms of factorials by the end of this video. So let's talk about choosing a multiset. Let's go back to the 7 dress shirts problem. You have 7 dress shirts and have job interviews on each of the next 3 days. How many ways can you select 3 of them to wear for the interviews? So let's label the shirts 1, 2, 3, 4, 5, 6, 7 like we did in the last video. And we assume order doesn't matter and repeats are allowed. So a multiset is an unordered set with repeats allowed. For instance, now we can put 1 in the set twice and 4 as another element, or you can have 3 times, or 2, 6, 7. These are all ways of choosing which 3 shirts you're going to wear if order doesn't matter, but you're allowed to wear the same shirt twice because you know you're going to be able to do laundry. So a multiset, formally, is a set along with an assignment of a positive integer called a multiplicity to each element. For instance, this set 1, 1, 1, 1, 4, 4, 5, 7, 7, that's a multiset. That's not an ordinary set because it has repeats. But the way we think of it is a set, 1, 4, 5, and 7, along with a little number called the multiplicity assigned to each element. So 1 appears 4 times, so sometimes we'll write times 4 as a little superscript of the 1. 4 appears with a multiplicity of 2, 5 with 1, which sometimes we drop that multiplicity, and 7 occurs 2 times, so it's 7 to the times 2. So these are 2 different ways of writing the same multiset. Here's another way of writing down multisets, by piling stones on the numbers to indicate their multiplicity. For instance, set 1, 1, 4 can be written as a table by writing down 1 through 7, and then piling 2 stones on the 1 and 1 stone on the 4. The total number of stones is the total number of elements of the multiset. And so we're looking in our shirt problem for how to distribute 3 stones across 1 through 7 in any possible ways. So you can pile 2 on 1 and 1 on 4, you can pile all 3 on 3's head, or you can do 1 stone in each of 3 different buckets. This piling stones model makes it a lot easier to count multisets, because there's another way of thinking of piling stones. And this is the sticks and stones method for counting the repeats allowed, order doesn't matter choices. What we do is we add a stick between each of the possibilities that we're choosing from. So if there's 7 different shirts to pick, we add a stick between each shirt, and so there's 6 sticks that we add. Now we can think of a distribution of the stones as a way of putting a certain number of stones in the gaps between the sticks. What this can also be interpreted as, if we lay the stones flat, as a sequence of 3 stones and 6 sticks in some order. So choosing a multiset is the same as choosing an arrangement or a rearrangement of 3 stones and 6 identical sticks. But we know how to do that. We know how to count rearrangements. There's 9 factorial ways of rearranging all 6 plus 3 different elements, the stones and the sticks together. And then we overcounted by the number of ways of rearranging the stones and by the number of ways of rearranging the sticks. So we divided by 3 factorial and 6 factorial here and get 84 for the final entry of our table. So now let's look at the general formula here. A multiset of k things chosen from 1 through n is a sequence of n-1 sticks and k stones. So the total number of sticks and stones is n-1 plus k. So we have a sequence of n-1 plus k total things. Sometimes we rearrange this and write it as n plus k minus 1 just to make it look a little nicer. And then we want to choose where the k stones go. So another way of doing our overcounting and dividing by factorials that we did on the previous slide is say that we're actually just choosing among the n plus k minus 1 positions which k positions have the stones. And so n multi-choose k is equal to n plus k minus 1 choose k, or n plus k minus 1 factorial divided by k factorial times n minus 1 factorial. So that allows us to finally fill in the last element of our table actually in terms of a choose itself. It's just a bit of a different choose than we had before. So now you try. Say you scoop a handful of 10 M&Ms out of a large bag of M&Ms. There are 6 different colors of M&Ms available. How many possibilities are there for the multi-set of colors in your hand? And that's all for today, and I'll see you next time.